So welcome everyone, thank you all for coming to another CFTC Seminar. Today we have the pleasure to have Professor Malte Henkel from University of Lorraine Nancy, which is a world expert in phase transitions, statistical physics, etc. So he's going to talk to us about the Schrödinger invariance and the water model. So please, Malte, thank you very much.
Thank you for the introduction. It's a very great pleasure for me to be back here to tell you some recent work done together with Schrödinger in Turkey. Okay. To give you some overview, what I want to say. First of all, we should put things a little bit into context, so I shall begin with a small reminder on physical aging, what this is, what are some main properties, what we want to study, and then there will be a long section on the Walter model. In particular, we shall present here the solution, the Walter model in d dimensions, that he will be a continuous parameter, not just 1, 2, 3, as it was common in the past. So this will be discussed in detail. Then follows a brief reminder on some dynamical scaling forms, and then we shall finally explain how the results we found in the Walter model can actually be explained as a consequence of the dynamical symmetry that is from the so-called Schrödinger invariance, which comes from the Schrödinger free algebra. This has to do with the fact that here in the Walter model we have dynamical exponent 2, which I shall explain, and then we shall actually compare results and then some conclusions. Most of what I'm going to tell you is on this paper here, of course in the archive. From time to time I shall also borrow something from other papers and very necessary information is in here. Okay. So, for the context, physical aging, I do not need to talk about the personal aging everybody experiencing every day. That is highly personal, difficult to reproduce, and very hard to study. I am interested in what is called physical aging, that is dynamically self-ordering processes in materials. Basically, you ask the kind of the question when you look at materials after some time. Why do they look old? What has happened to them that optical, mechanical, and other properties have changed over time? And it has been discovered by Dutch colleague Freud in the 70s that indeed physical aging, when you look at it carefully, indeed finds many reproducible and many universal properties. What he was actually doing, he was taking years-long experiments, taking some material, any kind of plastic, any kind of French cheese, any kind of metal he could put it, heat it up, then put it into a cupboard for a defined time, and then putting it on a machine and tearing and see how it extends. And the weighting has been done for a couple of years, the tearing has been done for a couple of years, so it was probably a 10 or 15 years project to have all these things together. And so the physical aging properties you find in many applications. Since we shall be interested in symmetry properties, there are 3 properties to be noticed. First of all, aging is a slow relaxation process, and slow means exactly this, not fast. And in a sense, I shall explain a little bit later. In particular, relaxation times tend to be infinite. In general, there is no time translation invariant, so this symmetry is absent, but there is an necessity. Then how do you find them? For example, when you consider simple magnets, people study this in classes, this order here, we want to study more simple systems without this order, take some simple magnets, some easing model, for example, and then many of these systems indeed show dynamical scales. In contrast to equilibrium critical points, you don't have to make a fine-tuning and find the critical point very precisely. That is not necessary. Rather, you do the following kind of experiment. You prepare your system, for example, in some high temperature initial state, disordered. Then you quench it either to a low temperature, then you phase ordering kinetics, or to through the equilibrium critical point and you have non-equilibrium critical dynamics. And since in principle can be any low temperature, there's no fine-tuning necessary. This way you achieve a non-equilibrium state. Then you fix the temperature, let the system evolve and study evolution. What generally happens is that in these systems there is some time-dependent length scale, and in those cases where this goes for large time, this algebraic, this defines the dynamic exponent first, and since it is a power law and not an exponential, that is another sign of slow dynamics. Z is the dynamic exponent. So what basically happens at the short time after the quenching is many small clusters, and at larger times these clusters are getting larger. And there are many, many experiments where this seems to actually see. It's also possible to look into non-equilibrium systems, which are intrinsically out of equilibrium, for example, systems of irreversible chemical reactions, but at a critical point now. And then you make the same sort of experiment. You prepare the system in some initial disorder state, you quench it onto the critical point, then you get non-equilibrium dynamics, and you let the system evolve and study the dynamics. Again, you will find there is some length scale growing algebraically. It defines for you the dynamic exponent. And what then is happening here, you see it's a bit similar to the clusters you had, but here the point is when you look at these things, here you see the clusters are slowly dissolving. It's not really the growth of all the clusters, but you rather get here a process of cluster dilution. Again, there's lots of simulation evidence for these things. Here I want to show you first of all a different way how to characterize aging, which is actually figures which I take from the water model, and I shall explain a little later where this comes from. What is the water model? Well, briefly said, you take two opinions, plus and minus one, and then you take the following, you select the spin, and you consider any of its neighbors, and the spin is taking the opinion of its neighbor. And that defines for you dynamics, and you can study the dynamics. This actually is a very paradigmatic model in systems without these patterns which are not relaxing to equilibrium. What people often do, they do not really look at the microscopic configuration because that is very hard. You rather look at correlators. For example, you could look at a single time correlation, so you take the spin at two different positions r and 0, so I assume spatial translation variance, but at the same time. And this gives me single time correlator. And so this single time correlator is plotted here over against the distance for small dimensions. And now you see several things. First of all, for different times, the curves are always moving up this way. Always here, up to the right. That is, for larger times, the dynamic is the correlator is decaying more slowly, so the dynamic is going slowly. Older systems are evolving more slowly. That is slow dynamics. The other property is, for different times, you get different curves. So there's certainly not a time translation invariance, but if you replot the same data, now over a rescale length, where the rescale is the square root of the time, then you find here actually a collapse of curves. I show you here three curves for three different dimensions for comparison. The same thing is happening in dimensions larger than 2. Then again you see the three curves in 3 dimensions here. It's slow dynamics because the curves are moving up with the time. It's definitely not time translation invariant, and you find again scaling products and you find scaling functions. The point I want to make is here that when you just look at these functions, they look indeed very different. The form of these scaling functions you get here below 2 dimensions, above 2 dimensions is very different, and that is something we want to come back to. The same thing you can also do when you look at the two-time correlator, autocorrelator, you go to the same space point, and you take the two different times, the time s and tau plus s, and here you plot the correlator over against the time difference. It's the same phenomenon. Curves are moving up this way, and the waiting time s is getting larger, so all the systems evolve more slowly. You get different curves for different values of s. So there's no time translation variance, and you find a scaling collapse. If you look in the inside here, you see it's actually are scaling like a power. And the same thing also happens when you go above 2 dimensions. You have again with the curves, moving up this way to a slow dynamics. They are distinct curves, and you find the scaling collapse, and again you see these curves are different. And of course, we want to understand why it is so. Okay, we are out of equilibrium. In principle, we are interested in string configuration, so we have opinion configuration sigma plus or minus 1. So these are provided with a certain time-dependent probability, and you write a master equation for this. Of course, the evolution inside the master equation is determined by these conditions. And one important property is the Lie balance condition, that is, when this is the equilibrium probability of a certain configuration space, you get this identity, which means that all these brackets here vanish separately. So that means that the equilibrium distribution is a stationary solution of the master equation. What we shall see in a moment that in the Rotor model, this property actually does not hold, but it is just element. Now, what do I want to tell you? First of all, we shall discuss the exact solution of the Rotor model after having defined it. This comes in a minute. Then we shall discuss the role of the space dimension, why it is important to be less than 2 and larger than 2. There will be something coming. And then we shall see how these correlators can be derived from Schrödinger invariance. I have to make a couple of hypotheses to do this. First of all, the response functions, which I also shall define for you, will be covariant under Schrödinger transformations, not the correlators. From this, we can then derive the form of these 2 and 3 point response functions, and then also then combine this with non-equilibrium field theory to derive the form of the principal form of the correlator functions, and then finally use the Schrödinger symmetry in a new non-equilibrium representation, which then allows to actually derive the precise form and compare with the experience. Okay, that is important. So in particular, we can then understand that the Rotor model is not something, in spite of the clusters in the inside are always frozen, it's not at all a low temperature phenomenon, but it is rather critical. Okay. After this introduction, let's go to the Rotor model. The Rotor model is, of course, as you all know, something very well studied, maybe to death. Of course, everybody thinks of the famous and unreadable book of Liggett. When I think of Rotor model, I think of the book of Tagliatone and Mario Oliveira from Sao Paulo. A fantastic book. It's a kind of book I would have loved to read when I was a student. And then it didn't, unfortunately, exist. Okay. The Rotor model is defined by the following choice of the condition bits, namely this one. That is the choice here, so that is the thing we want to study. Delta is here the nearest neighbor, left and right nearest neighbor, and that is the Rotor. Actually, in one dimension, it is identical to the kinetic Ewing model with global dynamics at 0 temperature, as you all know. So in a way, it is a generalization of this. Okay. And of course, the Rotor model has arisen in many different contexts. At least it goes back to the 70s. In biology, people already were discussing it. Of course, no mathematical treatment. It was then rediscovered by the physics chemistry a couple of years later in Geneva, in Moscow. Of course, the Rotor model, people claim it has something to do with opinion forming, maybe. It can also be used to describe systems of irreversible chemical reactions far from equilibrium, and actually it is claimed it's a very typical and very paradigmatic example for this. So these colleagues from Paris further exactly sober the aspects, Mario de Oliveira, Kaprisky and again, not least, and in particular, last but not least, a very recent series of studies of long-range interaction in the Rotor model, which also for the work I want to describe here has been very studied. So what is the Rotor model? Let's understand a little bit better what it is. So we do it at zero temperature. Here are the two opinions, blue and red, why not? And so, to understand what is the difference, say, between the two-dimensional global heating model and the two-dimensional water model, consider as an example this configuration, 3 blue spins, 1 red spin. So what is the probability for this one? In the global model, that this spin will enter blue as 1, and the other one is 0. In the water model, it's this one. So this already tells you that these two models are different. It's not the same thing. Global heating model in 2 dimensions has nothing to do with the water model. The other property, water model does not obey beta patterns. You see in the following way. For example, you could consider here a sequence of 4 configurations, and you can make the loop this way, or you can make the loop the other way. If you have beta patterns, the product of the layers is the same, and either way you go. If there's no beta patterns, as you find in the water model, that is not the case. So there's no beta patterns in the 2-dimensional water model. When we look into the evolution of clusters, here's a picture from the water model. For comparison, I take a picture from guided percolation, another non-equilibrium process. And you see in both cases here what you actually see, that these clusters dissolve. The cluster process is not exactly the same, but there's a couple of analogies, as you can see here. Water model clusters will only evolve at the surface. They cannot evolve in the inside there, and they're frozen. It belongs to non-equilibrium systems. There's no beta parent. It's not relaxing to the equilibrium state. But they show dynamic escape. The clusters dilute. Okay, it's a description of opinion forming. Okay, and in particular, when you look at the interfaces between the distinct opinions, then you see something very important. When you calculate the density of such interfaces in low dimensions, you see that with time it decays. When you do it at high dimension, it goes to constant. So you will always retain the concept of opinion in more than 2 dimensions, and in principle, any concept of opinion will disappear in low dimensions. So that is something which is in mathematical literature. People write a lot about, and it's something important to note that below 2 and 2 dimensions, the model does behave very differently. The very attractive feature of the water model I want to use, that it gives you closed systems of equation of motion. And since you know from statistical mechanics that is something which happens only very rarely. But the water model is one case. For example, if I look at the time evolution of a single spin, it can be written in terms of the transition rates, always at this kind of average, and this can then be evaluated and gives you this form, and you see it again. Single spin at some position. Maybe a bit displaced, but that's an infinite system which is closed by itself. And in the same way, you can also write this for the correlator. Of course, for the correlator, there's an extra constraint that when you take 2 spins at the same point, the square plus minus 1 is always 1. And so this constraint, to treat this, is a technical complication. Anything else is trivial. So the water model, you can see, it's a most naive simulation of the heating model, the global heating model you can do. That is what you want to do. But you pay the price that you have to give up the difference. Okay, so that is here. I skip this here, that is the derivation, how you get these identities. We go immediately to the continuum. When we go to the continuum, we have then here 2 spins at time t, at 2 positions. I put 0 here. So we get here a time space physical correlator of this form. And from the equations we had, we obtain the following equation of motion. So it is here, the change is here the Laplace operator, and I assume that we have rotation invariance, so I can write here the rotation invariant form, where now B is the number of space dimensions which enters here as a constant. Good. Then how do you solve this? The best and most simple way is to try scaling ansatz. That is, you say it is a function of the scaling variable, that the lambda exponent is equal to 2, so we get this one, maybe up to a quarter factor, and then that this works, you see that we get here a differential equation for the scaling function which only depends on the scaling variable and the nothingness. So that tells us that the scaling ansatz, which was a mathematical experiment, if you wish, works. And now we come to the one important mathematical observation of the whole talk. Everything else is really straightforward. The general solution of this equation can be written in this form. You have here two Kummer functions or confident hypergeometric functions. I write here n and u in the notation of a parallel statement. You get some exponential prefactors, and you have here two constants, which then have to be fixed, of course. It's a second order differential equation, so there will be a two-parameter space solution. So the important observation is here, and for the whole solution of the Rosen model, everything else will be just fitting in a second environmental system. That equation is very relevant. Before we can do this, nevertheless, we have to find this exponent here. This we do by looking into the stationary solution. So it is this one. When we are rotation invariant, that is what we have. And it's of course easy to integrate here this, and we have two constants here. And now we have to see the stationary limit, because we have a scaling variable, means that the scaling variable must be very small. So we have to look here in the scaling variable, what is happening for u small. So either when b is less than 2, it goes to a constant, or when b is larger than 2, it behaves like a power law. That actually reminds us here on critical correlators. So this exponent b, we can conclude as either of these values. And so we have to distinguish now between 2, below 2 and above 2, between these values. Actually, we shall see. Less than 2 is fluctuation dominated, larger than 2 will be mean field theory, and the other case is the arbitrary dimension. Okay, let's do the calculation less than 2. B is equal to 0, so we put it in. That is the form you get. And now we need boundary conditions. First boundary condition, when you look at the evolution of the water model, you have a certain length scale, but when you're looking at scales, last with respect to this length scale, everything should be uncorrelated. So, for large distances, this correlator should decay very fast, faster than any point. Which means that when we look at here, there is a constant. This will only decay when this constant is 0. And the other property is, well, when we put the two spins together, the spin squared is 1, so this should be 1. So let us see. The first condition fixes me this one here, the second condition fixes me the other one. So I can then write here the exact solution. Everything is in there. And u is a Trigonometry function, we had before. Please keep this form in mind, because we will see it coming back from a more general context later. That we have this form here will become very important, and you see here the dependence on d. And that we have this explicit d dependence will become very important later. That is something we shall come back to. Of course, you can simplify, you can simply write in terms of an incomplete dimension. For any d smaller than 2. And of course, the 1D case is of course to produce the very famous law of the the physical remark. When we do phase ordering kinetics, so we make a quench below TC, let's go for a minute squared in ferromagnets. So it's a standard leading model. Then we say there's something like Moore's law, which means when you look at the correlator here, the correlator as a function of distance is always decaying here linearly. That, for example, if you run the Glauber-Ewing model, when you copy the exact solution and simply expand, you will see this, it's decaying linearly. And in the 2D case, there's actually this figure here, correlator over the distance, and you see it's decaying linearly. Okay, so for ferromagnets, it certainly is there. What's happening in the rotor mode? If we make the same expansion, that is what we find. Or you see, we find this here. And this exponent 2 minus d is only 1 when d is equal to 1. That is exactly where we have theta balance. And in those cases, when we don't have theta balance, it's not 2. So Pohor's law does not hold in the bottom. You can also take it in the more original form and say, you look at the structure factor. So this will have this dependence here. In the water model, of course, from the exact solution you can work it out. That's what you find. And it decays in this way. That is equal to this one, again, only when d is equal to 1. So the water model, Pohor's law only holds when the balance holds, that is when d is equal to 1. Now we go to the other case, d larger than 2. We again analyze the exact solution, and we must do the boundary conditions. First of all, we say when R is large, this should decay faster than any power. And again, this means that this part here must disappear. C1 vanishes. And we look at here, it decays, but it only decays like a power, and that's not fast enough. So we need C1 equal to 0. In the other case, okay, when we now look what happens at smaller distances, that's what we find. And this means one thing. Here we cannot simply say when R is equal to 0, we cannot simply say, oh, the correlator should be equal to 1. That physically motivated boundary condition is here no longer compatible with the dynamic scaling under theoretic. Of course, in the literature, people know this for a long time. But they do differently. They say, okay, let's take a very small distance, and then they say there the correlator should be equal to 1. And they refuse to look anywhere else. Of course you can say so, but it's amounts to the same thing. So this boundary condition here, this condition is outside the scaling limit, we cannot use. So we have to accept that we have this behavior here. Okay, this we can fix an amplitude, and that's what we find. Again, you find the Jacobi function, this exponential here. You find that you get here different indices, and you can again write in terms of incomplete gamma function. Again, you see that it does reproduce what we know in 3 dimensions, of course. But here we see something, we get a common treatment for the two things, and if you want to find this constant here, you have to do differently. What you would have to do, go back before the scaling limit, solve the equation there, then show that somehow you get into the scaling, and then you can by comparison resolve the amplitude. A lot of work for non-universal amplitude, I do not think is worth it. Okay, summary, I showed you these plots before, and now you understand where they come from. So it's the same plot as I had shown you before, and now we understand that it's the exact solution where I derived it from. So that is there, and the scaling functions are indeed different for d less than 2 and larger than 2. But also you see, in a way, they look very similar. It's only these exponents here which are different. And that is something we come back to if you want to explain. Now, we do the same thing. We want to do the 2-time correlation. So we say 2 times here, in a certain distance. Again, we find there's a diffusion equation of motion. And now the initial condition, when the 2 times is equal, is a single-time correlator which we have already worked out. So this we use as an initial condition, and then we solve this differential equation. And this is easy to do. You just make a Fourier transform here and plug it in, and then that's what you get. You get this integral here, and you have to do this integral. So that is clear. It depends only on the scaling variable here, T over S. Nothing else. So it is indeed, you see the dynamic scaling is already in. And now we want to find the form of these functions. So then we have to do something with it. So again, when we have e less than 2, we know the exponent. Then for the u function, we use an integral representation. So that's what we get. And then you see here's a Gaussian integral you can do. You find this form here, and you can identify the hypergeometric function. So the important point is here that you realize there is some hypergeometric functions with some arguments which depend on d, and everything can be written down. Again, when we are on 1 dimension, we do indeed produce the known exact result from the global as it should be. So that is there. Please keep in mind that here for the two-time autocorrelator, we had this FQ1 Gauss hypergeometric function. And the same thing also happens in the other case. We larger than 2, we do the correlator, it's a double integral, and we write again as some hypergeometric function. The arguments have changed. Actually, it turns out that in this case there's a mathematical identity which allows you to write these in terms of elementary functions. And this is very interesting because these expressions, that is something you know very well from physics. So indeed, the Rotor model, in more than 2 dimensions, the two-term autocorrelator gives you back the autocorrelator of unity. That is what was mentioning here. So we get unity. So it's looking complicated, but actually it's not. Okay, again, I show you here these plots for the two-term function, and also there's something you see, and now you have understood where they come from. So it's just a solution here. So the scaling functions are distinct for above in 2 dimensions, of course. And in a similar way, you can also find the response function. So you calculate some average, you introduce some external field, look at the perturbation. So the response function again, you find a scaling form. It's looking this way. You see here a Gaussian form, which is a very typical thing for the Rotor model. The responses are Gaussian, although the model itself, in particular in low dimension, is not. So it is of course not excluded that certain observables take a simple form, while other observables take more complicated forms. So this completes the solution of the Rotor model in D dimensions. So we have everything. And it's very nice to compare, for example, with another model, the circle model, which you can also do in D dimensions, so you can compare and systematically see what properties hold, which properties are not, etc. Now I want to come to the second part of the talk to explain from a more general point of view where these figures come from. To begin, I make a brief reminder on the dynamic scaling. This gives a generic form. For example, the correlation function. We have some order parameter cos length. So then we expect here some scaling form here, some scaling function exposing before. So that is a general thing. Then we want to look at the autocorrelator. We set r equal to 0. Then we want to have a single time correlator. We set it 2 times to be. So everything in principle is what we have done is contained in the form here. B has its values here. When you do the response, you take the average order parameter, you introduce a perturbing field, you look at some sort of dynamic restrictibility. So that is the response functions. In field theory, you write this in terms of a response field. Janssen and Dominici theory, our good friend Cyrano from old days. He invented these things, and you can actually show that the response function becomes a correlator between the order parameter and the response operator. So that is actually here. And again, you have the scaling fields here, the A exponent is known, and all these things are known. For the asymptotics, then we look into the case when the spatial argument vanishes. Then for large arguments, we expect here some polar form. This defines an autocorrelator exponent or an auto-response exponent. And indeed, whenever we have initial conditions with short-range spatial correlations, then in general these 2 exponents are expected to be. So that is the background we need in order to attack the rest. Now, we are seeing the scaling functions. Now we want to understand, in the Rotor model, we have very specific forms of the scaling function, where we explain Trikumi functions. Where do they come from? I mean, when you have something like this, you cannot possibly get it from a very complicated, in general, from a very complicated model, you must get it from a very generic argument. And normally the generic kind of generic argument you bring forward is unsymmetry. And that is also what we look at. So we look into so-called Schrödinger transformations, which of course have nothing to do with Schrödinger, but they have to do with Jacobi and Pepli. about 100 years before. So what is a Schrödinger transformation? In time, you take these things here. So that is a fractional conformal transformation which you may know. So we have in particular time translations, you have dilations, and then you have something else. And in space, you find here translations, you find Galilei transformations, you find rotations, and that is very strange denominator. And this together forms a liquid, as you can check. And this is nowadays called the Schrödinger. Okay. When you get sufficiently famous, things are named after you, even if you're completely innocent. That's how it happens. So, in particular, when you look at the dilatation in time and in space, they can be parameterized in this way. So you see a factor 2 here, which means that the dynamic exponent is equal to 2. Okay, dynamic exponent equal to 2. Well, when you were to go into studying phase ordering kinetics, it's trenches to below TC, then you would say when we have a non-conserved order parameter of that model A type, then indeed it can be derived as V is equal to 2. That we know. So that is very natural and very relevant. When we do trenches onto the critical point, as we have to do the water model, because otherwise it's not scaling, that becomes a very serious restriction. We make this restriction nevertheless, but we have to keep in mind that this is a restriction which limits very seriously the applicability of what I'm going to say. First of all, this Lie group, the Schrödinger Lie group, is not semi-simple. So its representations are always projective. There's always coming, you make a transformation of coordinates, but you also must transform the wave function. That is something what you know when you go to non-realistic quantum mechanics. When you look how Galilei transformation is changing the wave function. That is one example which you may have seen. So you have here indeed non-relativistic masses appearing here, which from quantum mechanics, that's Schrödinger is coming from, that's coming here. And so this is a very important distinction from semi-simple group, like the conformal group, which is semi-simple and such factors do not exist. The Schrödinger group is indeed the most large finite dimensional Lie group which maps any solution of the simple diffusion equation into another solution of the same equation. That is also something which these gentlemen already do. Okay. Now, our principle will be the following. Now we want to apply this symmetry to physical systems. And then, of course, we have to say which objects are expected to transform covariantly under such symmetries. And now comes a very important point. We must make a restriction and say what is covariant are the response functions, not the correlators. The correlators are not covariant. These projective factors we have rather will impose for us that if we say covariant correlator, the correlator would simply vanish, which, as we have seen in the Rosa model, is nonsense. What is okay to say that the response functions are covariant, only the response functions. Then indeed, since response functions have to do with the response scaling operator, the scaling dimension indeed can be shown to be always the same as the scaling dimension of the order parameter. That is an important result. And then in particular you can derive the form of the tutor point response function, this one here. And so it is this one. You see here the Gaussian form, you see a power of P factor. It's a causality condition, of course. You will only see a reaction of your order parameter after you perturb it by the magnetic field. Very natural. So you have here this property, and you see that for the masses here, the mass of the response scaling field is negative. We have negative masses which are particles have positive masses, response operators have negative masses. That's a property of response operators. And then when you look at 3-point operators, which you shall need, for example, 2 phi, phi tilde, it looks as follows. You have causality conditions, you get a couple of core factors. These are written, you have written here the abbreviations. You find some Gaussian factors, and on top of it, some function which is not determined, but you know it only depends on this particular argument. Okay, so that is background what we know. Then how do we find correlators? Correlators you can reduce to 3-point functions. In the case where we now say we make a quench to the critical point, that is, the fluctuations of the bars are important, and fluctuations of the initial correlations are unimportant because they give only corrections to scaling the following form belongs. And you see here the temperature, that is the critical temperature. And you see what we have here are the two order parameter scales, and you have a response operator. And you see we have here this response operator. Phi tilde squared has to be considered as a component scaling operator, so we have to find the form of this triple function, which falls in this Schrödinger invariance is telling us. So in principle what we can do here, the non-vanishing correlator follows from this 3-point response function. So whenever we are able to give the full time-space form of the 3-point response functions, we can continue. And that is why we are restricted to equal to 2, because it's only in this case I know what the answer is. And now last point, which is very new, and this is changing matters. When we try the symmetry representations, we cannot use the standard representation. What we have to do, we must, when we want to apply them to non-equilibrium statistical physics, we must go to non-equilibrium representation. That is, when we take here some equilibrium generator, we must make a Bayes transform, so that is a matrix, so that is transformed in this way, and we then get here a non-equilibrium correlator, and then we transcribe this to correlation function. It means that the equilibrium form will pick up this particular factor here. And since we say this W is taken here this form, logarithm t, times some constant, we get here these 3 parameters. Other words, the scaling operator, which at equilibrium was characterized by single conformal dimension out of equilibrium, is characterized by a pair of 2 scaling dimensions, which have nothing to do with each other and which can be very different. That is the new aspect. And in the same way, the component response operator is not only characterized by the conformal one, but also by this one. I take in the factor 2 out by 2. So we get here this thing. Then, with all these things together, Schrödinger variant is just long enough that we can find the correlators and now Schrödinger variant. Get here here. For non-equilibrium critical elements, where the bars is dominating, and z equal to, we find the following. The single time correlator, which is this here, is taking this form, up to normalization constant pattern. So what you see here, you see this exponential factor, and you see the Tricomi function. And that is something what we have seen in the Rosen before. It's the same structure which was appearing there. And you see that we get here 2 new critical exponents, which will determine for you the shape of the scaling function. So we define the 2 new non-equilibrium critical exponents which have no analog at equilibrium. To be able to get this. Good. Then we do the 2-time autocorrelator, can also be written down in terms of a so-called upper hypergeometric function, which is probably a little less familiar to you, but in those cases, when it so happens that this identity holds, which in the cases I'm aware of always happens to be the case, I don't know why. If that happens, this form simplifies to this one here, and you recognize the Gauss hypergeometric functions and you get certain parameters. And that also should remind something of what we've seen before. So, the form of the scaling function will only depend on these 2 critical exponents. These 2 non-equilibrium critical exponents. Let me show you here very briefly how you get it. So you want to find the single-time correlator, which actually you get is the 2-time correlator taken times equal. So, what you want to say, you set the first term, t minus epsilon, make it a little bit smaller for the moment, and send epsilon to 0 whenever you can do it without any risk. And okay, you have the scaling function. So, with two-time correlator, then look the following. From the expressions we have, these are the quadratic. We have these factors here from the 3-point function. We have the two exponentials, and we have the unknown scaling function which we had. And since we go to the new representation, we get this and this extra factor. So that is the origin where this integral comes from. Okay. Now this integration, this quadratic condition simply means that we integrate up to t, and that's it. What we will do here, we make a change of integration variable, small r is fixed. So you and you can then also the time integration you can escape. So, and this integral falls apart into things. You get one integral over r, the small r is a factor drops out, this drops out, and you have this factor here. So, now you send here epsilon to 0, so this means this can at most be a constant, if it is not 0. This tells me, this epsilon factor tells me here that these two things have to be equal, that is a constant. Otherwise, I would either find 0 or infinity, I cannot use. So I get these restrictions here. Okay, what do I have? I have these various big vectors. This first exponential is here, and I have this Gaussian integral. This I can do. Here it is. And then I recognize the Gaussian trichotomy geometric constant. So you look up in popular collections and you find this one. So that is how you get there. And now finally, I give you a list of models where these predictions can actually be checked and the various exponents we expected. That means we do it similarly for the single-time correlator, for the two-time correlator, and for the two-time response. So we have just a very few parameters to describe all of them. So delta and the various size. So the form of the last two is just given by these two parameters, and here's the list. Of course, this includes the Glauber-Eating model in one dimension. And you can read off certain values and the two observables you get. We discussed in detail the model model, below 2 and above. You could also do the case at 2, it's a technical dimension. Okay, so again you see the various values can be obtained, in particular the exponents you find here look very trivial indeed. Let's face it. In the third model, you can also do the calculation. Above 4 dimensions, when you are mean field, you see you find the same exponents. Yeah? The Edward-Wilkinson universality class. So when you do surface codes, Edward-Wilkinson model is another very well-known model. You find these values as mean field. There are variants of the contact process, or the right calculation, the bosonic way, where you can pile up particles arbitrarily. That is also solvable. It's the same universality class as Edward-Wilkinson. Or you could look into the case of pair contact process below a certain critical threshold, and you can find the values. When you do surface code, you can write a generalization of this, which is the same relation which has the circle model to the even model, so that's the so-called Architecture model. Below 2 dimensions you find non-trivial values, above is mean field, and then finally at the critical point is the multi-critical point, so you get the tri-critical mean field, and it works in the same way. So in all of these cases, the formulas I was showing you with the use, etc., can be confirmed, and you always end up with the same consistent identifications, of course. For each universality class, you will find different values of these universal exponents. And this brings me to the conclusion. We started from the recognition that dynamic scaling is the basic essential building block of the calculation. Everything is built around it. And in particular, the water model we have been looking at, which indeed satisfies dynamic scaling for all dimensions larger than 0, the dynamic exponent equal to 2, and we have to have We check that it does satisfy dynamic scaling, and we work out the explicit solution for correlators in full detail. In particular, it's a case study for non-equilibrium dynamics, because the noise from the heat part is dominant and not from the initial state, and it would be the case if we were doing phase ordering kinetics below the heat. So it's really, it has no surface tension, as you can know from the literature, but what you see sometimes that it should be related to phase ordering kinetics. To me, affirmations of this sort make little sense. The important thing in our comparison was that the generators we were familiar from equilibrium have to be brought to non-equilibrium form in this way, in this particular choice. If you want to hear more about this, I shall be talking about this on Tuesday in the Instituto Superior Técnico. So those who want to hear more about this, I'm cordially invited to come. Let me say one word at the upper critical dimension, then it is not this choice, but rather this one, log of log. But anything else for the same correspondence also goes through. I have no time to go into this. And so we see that Schrödinger invariance becomes a very natural non-equilibrium dynamic symmetry, at least when the dynamic exponent is equal to 10. We have to admit the covariance of the response function, only of the response functions. Then correlators can be reduced to certain response functions. And you can then use these non-equilibrium representations, like the similarity transformations, to arrive at explicit predictions. Okay, and then we have seen there is a class of new, so far unsuspected non-equilibrium exponents, which I call here delta to tilde, c to tilde, which are related to the scaling behavior of the response operator. So the most exotic, the most remote thing is somehow described as a coupling of the system with the level, which is involved in this. Which then defines the properties we need to get the scaling functions. And to finish, I want to recall a day long time ago when I was a student, and when then Wittenberg and Bonn made us read a book, Filmer, on Lie groups and these things. Very good book, very much to be recommended. And at the time, I was very much impressed by a sentence he wrote in his preface. We are looking forward to the day when Lie groups can be pushed to give the dynamics of a physical process. And here you have an example. Thank you very much.
So, questions?
Thank you for your presentation. I had a question in particular, I guess it's a kind of broad question, but it's related to specifically the fact that you observed this symmetry for a dynamical exponent of z equals to 2. Since that dynamical exponent is related to growth processes, and you even showed several examples of growth processes.
Yes, I mean, the dynamic exponent, first of all, you must know that you're in a case where you indeed have an algebraic growth of the length scale of your order classes. That is one thing, somehow the physics must tell you, this is something I'm assuming here. Yeah? So that's if that is, for example, logarithmic, things like that. Okay. Here I say the Schrödinger proof by construction, at least in the representations I'm looking at here, is equal to 2. As you see when you look at the scaling behavior between time and space, that is simply what you read off. Let me show you this again if you want. Not just the wrong direction. Here. So that is here. So you see here, you scale the time is delta squared and the space is delta, and so the ratio between the two gives you exactly the dynamic exponent. That's where you read it off, and that's where you know that the dynamic exponent and this representation is equal to 2. What you can do is to look into representations of the Schrödinger group where we have different values. That is also possible, but I do not know yet what are consequences of it. That is also something which needs to be explored. It's an open question, and maybe in a year or two I can say more about it. For the moment, I haven't even started looking into this. But the difficulty is, of course, when you take different values and two, that the general phenomenology can be much more general than the cases we have been looking into. And that can also happen. For example, I have very strong reason to suspect that you don't, when you have at a critical point, we have a dynamic response different from two, that it's not standard conformal theory what you need, but so-called logarithmic conformal theory. And this can be extended to Schrödinger invariant, that is possible. But how to exploit the symmetries really is not 100% clear. We know a couple of examples where these logarithmic interpretations can be fitted to data. So, like the direct calculation, like the PV equation, like using 2 and 3D, that is possible. But, I mean, again, this is an observation which you make a fiction on the data. We do not prove here anything. We can just say it looks consistent. If you can come up with any good idea why it should be logarithmic or either doublet or triplet or what else, that would be indeed very interesting. Here is another question, very wide open for investigation. Does this answer your question to some point?
At least from what I gathered, I guess the challenge is specifically for the critical dimension.
Yeah.
So then Z equal 2 is somehow related to the formula equation now we have. So if you have Z different than 2 or some other dependent, then you don't know what is the
No, I don't know.
But this Z2 is related to that form at the bottom Schrödinger equation?
Yeah, it is
different, then the equation is different.
This equal to 2 is indeed this one. Yeah. And if you take a v different from 2, then you do indeed get a different equation, and you must study afresh what are dynamic symmetries, if any. And then, if you find anything of interest, what do you know? And again, that is a question still very much wide open. I know about one case when you don't have 1, 2, but 1, and you don't have really a normal derivative, but some non-local fractional derivative. Then that is a class of models which are called diffusion limited erosion, and then indeed one can construct a whole series of dynamic symmetries. And this has been brought to the point that some point of the response functions has been done. Correlation functions I have not tried to calculate in this way. That's also something which has to be done. And so for anything else, even the symmetries which might exist are not known, as far as I know. So you see, we are just scratching here a little bit the surface. And there's probably much more below, and it's okay. How much time it will take to dig this out, I don't know.
More questions? Maybe I have a bit of a naive question. I mean, at the start you said the temperature was 0, right? Is that all it is for
the temperature is zero in the global.
In the global?
In the global,
okay. But then here you do have temperature then?
Here I would at a critical temperature which is assumed to be non-dimensional.
Okay, because outside of the temperature is not as relevant, let's say, or...
The value is not relevant at all, it's only relevant when it is 0, so I can really separate critical correlation from the bars, but the correlation from the bars are important, and the correlation from the initial state is important. This I must be able to distinguish. When correlation from the initial state are important, everything changes. And actually, even the reduction here to a 3-point function is not good enough. You must do a reduction to a 4-point function. And what this means for the correlator, I'm still working on it. It's in the Moulin and okay, later. That is another installment will be coming to Nancy in May, and we hope to make that published. That is great. So here again, very many things are open and are not clear. And even for legal to do, not everything is understood.